Hello everyone, I'm Manuel Bardiès and I'm going to introduce you to the nuclear medicine dosimetry formalism. So first my declaration of interest. Then we're going to study today the MERD scheme. So MERD stands for Medical Internal Radiation Dose Committee. It's a standing committee of the American Society of Nuclear Medicine. It publishes through the Journal of Nuclear Medicine different type of documents, MERD pamphlets, you see there's 29, that are describing the means to solve a given problem. For example, formalism was displayed in a MERD pamphlet. Then we have dose estimate reports that are describing the irradiation delivered on a model for given radiopharmaceutical. Then there are 3 books, and we're going to discuss these books more in detail. So the reference book published by the MERD committee are, first of all, the primer. So the primer is a book that tells you everything about the MERD scheme and the MERD formalism, how to compute absorbed dose in nuclear medicine. Then it was published initially in 1988, revised 91, and then there's a very recent one at the end of 2022 that I warmly recommend getting. Then the MERD radionuclide data and decay scheme contains everything you want to know about radionuclides, what they emit, half-life, type of radiation, percentage of emission per decay, and so on. And you can, because it's also an ICRP report, so you can download that from the ICRP web pages. And then for those of you interested in dosimetry at the cellular level, there's a third book, which is the MERD cellular S value. So you have here MERD primer, the radionuclide data and decay scheme, and then you've got the MERD cellular S value. So let's go for the formalism, and I'm going to use the formalism as displayed in primer 1991. So assume you've got a point source of radiation that emits isotropically in all the space around, and the emission is initial energy is E0. If at a distance x from the emission point, in a very small volume, and I'm not saying a differential, but I'm getting very close, you've got the absorbed energy, which is E. Then you introduce the absorbed fraction as just the ratio of E divided by E0. And as you can see, because it's an energy divided by an energy, the absorbed fraction is dimensionless. However, you may want to compare the absorbed fraction in different media, in which case you will divide the absorbed fraction by the small mass dm of that small volume in which you score the energy deposition. And be careful, it's a small phi, a big phi. Big phi is the specific absorbed fraction, and it's usually expressed in gram minus 1. So because the irradiation is coming from usually systemic administration of radiopharmaceuticals, so we are making a generalization to a volume where you have a source volume and a target volume. In that case, you have the average absorbed dose in the target K from the source H, this is how it's written, is the energy absorbed in the target E divided by the mass of a target Mk. And you have here, coming from the previous slide, how to express the mean absorbed dose over the target volume. And then comes a very important concept, especially for molecular radiotherapy, the concept of penetrating and non-penetrating radiation. Assume that some radiation range is so small that you can safely assume that everything that is emitted is absorbed locally. Then there's a transcription of that in the MERD formalism, which is that the absorbed fraction for non-penetrating radiation in the target K from the source H is 1 whenever source and target are the same. And obviously, it means that the absorbed fraction for non-penetrating radiation is 0 when source and target are different. Obviously, this is going to depend on the organ size and particle range. So you need to have a radiation range that is much, much smaller than the organ size to be in a condition of non-penetrating radiation. The traduction per decay on the absorbed dose is that the average absorbed dose in the target from the source is just going to be the emitted energy divided by the target mass when source and target are the same, and it's going to be zero otherwise. So you can see the importance of penetrating versus non-penetrating radiation in a concept of molecular radiotherapy, because you really want to be in a context where everything that is emitted in the tumor is absorbed in the tumor, and you will be no irradiation elsewhere in other places than the tumor. Obviously, this in real life, you can safely assume that electrons and beta radiation are non-penetrating at the organ macroscopic scale. But bear in mind that they can become penetrating radiation at the cellular scale. Then this was made for monoenergetic emission, but obviously in real life you have emission in a radionuclide decay of a range of radiation of different energy and different particle. You can see here that for technetium-99M as an example. And obviously for dosimetry you have to take all these emission into account. So even though you can sum all the emissions to derive a sort of average energy emitted per decay, that's not going to help you a lot in dosimetry. Because in dosimetry, you will not have an average energy with an average range. You will have to consider all the emissions one by one, and for all of them, the emitted energy and how it is absorbed in the target, which you have here in that equation. So this equation gives you the absorbed dose rate in the target K from the source H at the time t, which is the activity in the source H at the time t, multiplied by a sum for all the type of radiation, of a probability of emission, the energy emitted for that type of radiation, and the specific absorbed fraction for that radiation from the source H to the target K. And because the energy is in joule, because the specific absorbed fraction is in kilogram minus 1, and the activity is in becquerel, what you have here are gray per second. Okay, then we have the absorbed dose rate at a given time. So you want to integrate that in time. So these are the equations you can have. And you end up by integrating all this to get the mean absorbed dose in gray in target K from the source H. Then we move, and I want you to pay attention to this, we are putting outside of the integral everything that we assume does not change in time. It's a very important assumption because we are assuming that, for example, the geometry is not changing, so the specific absorbed fraction is not dependent on time. It may not be the case. So in which case you have to follow the activity in time, and you have to sample to get the time integral of the activity or the cumulated activity. And be careful, obviously, time sampling matters to make sure that you really sample correctly the time activity curve. And you end up by defining the cumulated activity or time integrated activity in becquerel second or microcurie or curie per hour. So this is a way to compute the time integrated activity, because we know that after the uptake phase, that can be very quick, then the decay of the activity decreases because the vector is washed away. So that's because of a biological component and because the radioactivity normally decays in time, and that's a physical half-life. So you introduce here in that equation a constant, an effective constant that combines the physical and biological component. And so by doing so, you introduce also the effective half-life, and the effective half-life can be computed by, so like the inverse of the effective half-life is the sum of the inverse of the biological half-life and the physical half-life. And this has consequences. Be careful. The effective half-life is always smaller than the smallest of the half-lives. As an example here, you got 8 days for iodine 131 and a vector that's got a biological half-life of 2 days that gives you an effective half-life of 1.6 days. So time-integrated activity, if you just compute and so you have step-by-step computing, you end up with the time-integrated activity or cumulated activity in the source H is 1.443, the inverse of log 2, multiplied by the initial activity in the source. So be careful, it's not the administered activity, it's the initial activity in the source H multiplied by the effective half-life. So now a concept that is quite often difficult to get, that of residence time. Suppose you want to compare the cumulated activity for 2 patients. You inject the same activity, but in 2 patients, it's not exactly uptaken and eliminated and washed away in the same way. So you may end up having different cumulated activity in patient A or patient B. Likewise, the fact that you have the same cumulated activity for 2 patients does not mean much unless you have administered the same activity. Hence, the relevance of comparing the cumulated activity or time-integrated activity with the administered activity. And here, the introduction of a ratio. But by doing so, you have Becquerel second divided by Becquerel, so you have something that is expressed in second, so that's a time, and it's called the time-integrated activity coefficient, or more easy to understand, a residence time. So here are the Murd equations. So you've seen that one. So the average activity in target K from source H is the time-integrated activity in the source multiplied by, for all the type of radiation emitted, the product of probability of emission, energy emitted, specific absorbed fraction. If you group all the terms independent of time, you can introduce the so-called S factor or S value, which is the mean absorbed dose in target K per decay in the source H. And that is expressed in gray per Becquerel per second. And so we get the simplified equation, D equal AS, or for a given product, the average absorbed dose divided by the administered activity, which is a product of the residence time by the S value. So be careful, because whenever you use the S value, you enter a different world, and that is the world of model-based dosimetry. Because obviously these S values have been obtained not for your patient, but for a reference model, usually representing a reference patient. And that was very, very useful in a context of reference dosimetry for diagnostics. So you have here model-based dosimetry. There's an example of a recent model. So you have a voxel-based model, very nice looking, but it's not your patient. It's a reference dosimetric model. You compute S value. So for one isotope, you have the same S value because it's the absorbed dose in the target per decay in the source. So the pharmacokinetics does not is not part of that calculation. S value is per decay. But then you have to do a lot of computation, because for every source in the body, every potential source in your reference model, you have to compute the S value in the different targets. And then you need to have as much accuracy as possible, because this is a calculation for reference dosimetry. So usually S value are pre-computed, and you're going to use software that use this pre-computed S value. And that is opposed to image-based dosimetry. For image-based dosimetry, even though in both situations you will derive the activity based on images, but in one side, for model-based dosimetry, you will use pre-computed S value. For image-based dosimetry, you will use the geometry of the patient and the activity present in the patient to do a specific calculation of the absorbed dose for that very patient. And so you understand that model-based dosimetry, as I said, is quite often in the context of diagnostics, and image-based dosimetry is most often in a context of therapy. in the context of molecular radiotherapy. Bear in mind that we are still using the MERD formalism, right? Both for model-based or for image-based dosimetry. So the work of the MERD committee over all those years was, first of all, providing us with a calculation scheme. Whenever we're using D equal AS or whatever, it's been written. I mean, that's computation scheme has been given to us by the MERD committee. And then they've been doing a lot of S-value calculation for reference models. They used to be mathematical model, now they are voxel-based model. You also have NURBS, surface-based models. So the models can be more and more refined. And that started, back in the 1974. And now you have a production of new S-values. So using the MERD scheme, basically we're not, every radiopharmaceutical is administered and goes in different places. I mean, that's the objective of nuclear medicine, to have an image of different places for different purposes. So obviously, you will have to define for every clinical application where the sources are and what is your target of interest. So I'd like you to really bear in mind that you don't really have a choice of the sources. The sources are where the radioactivity goes, but you do have a choice of the target. You can say, or the clinician can say, I want to compute the absorbed dose to the liver, I want to compute the absorbed dose to the kidneys. So you do not select where the radioactivity goes, where the source is, but you do select where the target you want. And then this is the practical MERD equation that says that for a given target K, the average absorbed dose to that target is the sum of all the contribution of all the sources where the radioactivity is in the patient. In other words, for a given situation, say here you want to get the absorbed dose to the liver, you have to take the contribution of the radioactivity that's going to irradiate the liver from the lung, from the heart, from the liver itself, from the kidneys, from the intestine, and so on. So the algorithm, so to speak, for that equation would be to say, for each target K of interest, and again, you're selecting the target of interest, you identify the sources, you derive a time-integrated activity or time-integrated activity coefficient, accumulated activity residence time for all the sources, and then you select the relevant S values and you sum all the contribution of the irradiation from all the sources to the same target K. And you got some software, previously Olinda, but still, you still have Olinda as a possibility. You had Murdos, now you Olinda, IDAC, MerdCalc, which is free. They do that for you. So as a conclusion, the MERD formalism is valid for both diagnostic and therapy. I think it's very important to bear that in mind. The MERD S values, it's an impressive database that can be used for diagnostic, mostly, as tables. And these are used to derive the dose estimate report that I have not discussed in that lecture, but you may see in the literature. It's mostly for radiation safety. It's for a model rather than your patient. Then, patient-specific dosimetry, in therapy mostly, requires quantitative imaging and time activity curve fitting. So that's based on images. And then patient-adjusted S-value sometimes, or better, direct absorbed dose or absorbed dose rate calculation based on the geometry of a patient, the density given by the CT, activity given by SPECT or PET. Therefore, the MERD formalism is something different from the MERD S value. You can use the MERD formalism even if you compute your own S values, if you're not happy with the S values that are available in the literature, for example, because you have a specific geometry. Therefore, writing dosimetry was performed using the MERD formalism is not sufficient. It's needed, but it's not sufficient. You really want to explain how you derive the accumulated activity, how you derive the S value, or how you computed the absorbed dose directly. So you have to provide all this information to make sure that your clinical dosimetry is traceable and can be reproduced by somebody else. So here are some links. Obviously, one is on the nomenclature of the MERD that's currently being used, and some references on the MERD committee, on MERDsoft, where you'll find MERD Calc, OpenDOS, and so on. With that, I thank you for your attention.